Hello, everybody. Hopefully, everybody can hear me. Chris, you can give your hands up if you can hear me.
All good.
Excellent. Good. We have attendees coming in. It's only 13:03, so we'll give it another 2 minutes, maybe, if that's all right, just before we actually start. But lots of people probably taking their lunch, driving their cars, whatever they're doing, listening in the background attentively. Okay, it's coming up now to 13:05. So I think we'll probably get started. I think, yeah, there's a good few attendees there. Anyone that comes in, then we'll just join Chris as we go along, and it'll be fine. So look, uh, thank you very much, everybody, for taking the time out today to join us. My name is Jeff Ahern, and I am on the committee of the Irish Refrigeration Institute. It's my first webinar ever to host, so I'm chuffed with that one. Something new for me too. I want to thank our sponsors, as always, for facilitating this and staying with us, and indeed all of our members. So today webinar is run by Chris McGurn, and Chris is the area sales manager for ABB. Chris has over 10 plus years in electrical and mechanical, and is a mechanical engineer with an MEng. Today's discussion is going to be around energy efficiency in motors and drives, in particular HVAC and OR, and optimizing performance. The slides will be available afterwards, so if any people late joining will get to see them as well, and we will put them up. Karen and I will put them up afterwards. So look, without further ado, what I will say, sorry, one more point on that is, if you have questions, please do put them into the Q&A, and I will get to them afterwards, and we'll get together with Chris, and Chris can hopefully answer them. So without further ado, Chris, off you go.
Thanks a million, Jeff. I'm going to start off by sharing my screen here, so perhaps you'll just confirm that you're able to see my presentation as it comes up. So we should be on the energy efficiency slide, just my title slide, so hopefully everybody can see that.
I can see that, yeah.
I suppose, good afternoon, everybody. My name is Chris McGurn. I work for ABB in the motion division of ABB. What does that mean? That means I work with ABB motors and drives. Today, I'd like to thank the guys at IRI for inviting me along to be able to talk today about energy efficiency in the HVACR industry. And yeah, today I'm going to talk a little bit about how you can optimize the performance of your HVACR systems through the use of motors and drives. So initially, this is just a little agenda of what we're going to talk about. Firstly, I'm going to introduce myself, although I think Jeff has done that for me. Then I'm going to talk a little bit about energy consumption in the HVACR industry, some typical applications that motors and drives are used for in the HVACR industry, and how we can save energy through the use of variable speed drives on those particular applications. Then finally, I just have a separate section on some of the motor efficiency regulations that are currently in effect in EU, and then finally we can finish off with a little Q&A if anyone has any questions that they'd like to have answered. So yeah, this is just a little bit about myself. My name is Chris McGurn. I work as area sales manager for ABB, based in their HQ in Sandyford in Dublin. I've been working in this industry for around 10 years, although specifically with ABB for the last 3 years. I have a master's degree from Queen's in Belfast, and I'm also a chartered engineer with Engineers Ireland, and those are just some of my contact details and my LinkedIn details there. So this will be shared afterwards if anyone wants to reach out. So firstly, we're going to talk about energy consumption in the HVACR industry. So according to our research, buildings are responsible for 40% of the energy consumption and 36% of the EU CO2 emissions. So that's a fairly significant level of energy consumption that are coming just from buildings around the world. So roughly 10 to 20% of the total end use energy goes into the heating, ventilation and air conditioning applications. So you're looking at 20% of that large percentage is specifically especially in the HVAC/R industry. So because of that, it has become a focus point both with manufacturers like ABB, like ourselves, who produce motors and VSDs, and with the end users who want to provide, who want to lower their energy consumption, lower their CO2 emissions, and become sort of on the forefront of the green wave that has taken over and most industries these days. So what is the role of the HVAC/R system? So people spend 90% of their time inside a building, and both people's health and productivity is affected by that air quality. So the temperature and ventilation rate correlates to productivity of the people that are working in these offices, in these building spaces, and the ventilation rate also correlates to the amount of sick leave. So it does having a suitable HVAC system ensures that your employees are working as well as they can, and to improve their health and safety when they're actually working in the workplace. So poor air quality is a direct result of a poorly designed or managed HVAC/R system. So an energy efficient HVAC/R system is generally made up of several different parts. There's the dedicated design of the system itself, taking into consideration the layout of the building, how many floors it has, how many rooms they have, the size of the rooms, what temperatures they need to be kept at, whether there are people in the rooms or maybe they're trying to chill certain items, that type of thing. So that's one element of it. The equipment, they have to make sure that the equipment that you're selecting is properly sized and is meeting the current regulations around energy efficiency, and ensuring that they are working to the best of their ability. The way you control that equipment as well. So if you have motors that are running fans, that are running pumps, compressors, chillers, it's important that you control the way that those are run so that they are working in the most energy efficient way possible. So this improves your energy consumption, but it also lowers your energy bills and ensures that you're working as efficiently as possible. The occupant behavior is an important another part. So it's important to make sure that your people are aware of how the energy is used, that they're not running HVAC systems with windows open or jacking up the temperature just because it's because they're particularly cold that day, that type of thing. So it's important that they're aware of how to be as efficient as possible when they're running this equipment. And finally, energy monitoring and maintenance. So it's important that the equipment that you use is being monitored, so you're aware of how it's running, and without that proper knowledge, it's impossible to improve further on your energy efficiency. So this is an interesting slide that was sent to us from the factory. It sort of shows a breakdown of how much commercial energy is actually used in the HVAC/R industry. So you'll see here over 50% of a commercial building's annual energy consumption goes into the HVAC/R, into heating, into ventilation, into refrigeration. And within that, 99% of the time, the buildings are actually operating at a load below 80%. So the machines themselves tend to be designed in a way where the efficiency is stated at 100% load. But that is very rarely the case. You very rarely have a motor, have a machine, a fan running at 100% load all the time. In general, it's running below that load. And if you're running at 100% load, if you're running at below that load, it can have an impact on efficiency. So nobody specifies the efficiency of HVAC/R systems at part load. And when the part load efficiency is significantly lower, building owners never realize the savings that were calculated. So again, you need to consider your system as a whole. When you're considering your fan, your motor, your drive, your complete system should be considered, and you should understand what speeds, what loads that your fan needs to be running at, so that you can maintain a proper control over your HVAC system. And if they're designed not to run at part load, if they're not designed around an understanding of that part load, there can be a lot of losses within the efficiencies themselves. So it's important not only to consider the efficiency of a powertrain, but also the system efficiency of the VSDs through the power and the harmonics. So I'll talk a little bit more about harmonics later, but Choosing the motor technology for efficiency is important because, like I say, most motors, the nameplate on motors is shows an efficiency level which generally meets the regulation, but the regulation is stated at a DOL, at a direct online, full speed, 100% load situation. And only in that situation will you meet that required efficiency. So if you're running your motor at slower speeds, the efficiency of the motor itself will actually drop off. So it's important to consider. What speed your system is actually working at, so you actually understand what efficiency you're reaching here. So depending on the different types of motor you use, which I'll talk about a little bit later, you can see differences in efficiency. So this is a standard induction motor against a SynRM, which is our sort of headline high efficiency motor. You can see at lower loads here, at lower speeds, there's a drop off in the induction motor of the efficiency levels that it sees. Whereas in a more highly efficient motor, you can see it doesn't drop off quite as much. So you're able to get those savings by using a better level of equipment of motor. So how do people run their systems at part load? There are different ways of doing this. Traditionally, in a pumping system, um, traditionally people would have used mechanical systems to slow down the speed of the fluid that they're pumping. They would have used throttles. They would have used mechanical butterfly valves, that type of thing, which physically slows down the water and physically slows down the flow. But the problem with that is that the motor itself behind that, the motor and pump behind that, are actually still running at full load. So they're running at full load, just trying to push past that blockage that the throttle puts in place in the pump. So they are still running at relatively high loads whenever the requirement from the system is only maybe 70, 60, 50%. Whereas if you were to look at maybe electrically controlling that, which is through drives control, through a VSD, it means that you can bring the speed of the motor down physically without having to block the pump itself, which in turn brings the amps down and therefore uses less energy whenever it's running. So there is a benefit to electrically controlling the speed of the motor and the pump rather than mechanically doing it. And again, in some fan array systems, in HVAC systems, sometimes people use or companies use AHUs. There's potential to achieve higher efficiency in the system with multiple fans running close to their peak efficiency rather than one large fan controlled over a wide operating range. So it's sort of this is sort of just telling you to be careful of the design of the system that you're looking at. It's not always better just to put a big motor and a big fan on to run a specific system. Sometimes it's better to break it down into in this case 6 different fans that are more easy to control at the peak efficiency load and will provide more improved efficiency savings. So yeah, overall, you need to take a sort of a macro view of your system as a whole. In refrigeration, for example, in cooling, you need to consider the whole system in order to optimize it. If you start controlling the condenser, it can also affect the compressor, can also affect the evaporator. So you need to have a balanced system approach between all these systems, and sometimes being able to measure these systems individually, perhaps through digitalization of sensors, can help you monitor what's actually going on and understand where the base savings are. So this is sort of just a diagram of how you could control that, where you have a monitoring system taking a look at some cooling tower fans, some condensers, chillers, circulators. And if you have a dedicated team that is monitoring this at all times, or keeping an eye on this, it helps you notice, I suppose. Like in this case, you can see that the chiller compressor is using a high level of consumption, and using that knowledge, you can go back and have a look at that particular application and see if there is a way that you can improve the efficiency of that, which will improve the overall efficiency. So this is a little bit about power quality impact on efficiency for buildings. So this is about harmonics. So I'm not sure how popular harmonics are in the HVAC industry. It's a big word in the utilities, and we tend to focus on it quite a lot in some of the utility pumping stations that are used on water sites. They tend to use very big motors, maybe 500 kilowatt and above, that are running all the time. So back traditionally, not many buildings were run on non-linear loads. 20% of buildings were running non-linear loads back in the late 90s. What are non-linear loads? Those are loads that are taken from the likes of VSDs and other rectifier changing systems that consume energy. So LED lighting, TVs, computers, chargers, anything that's got a power supply to it. What does that do? Basically, any AC current that comes into a building follows a sinusoidal and up and down pattern, and that's the ideal sinusoidal load that the systems want to see. But whenever you're running these non-linear loads, it tends to distort that sinusoidal load that's actually coming into the systems, and when you distort that load, it kind of affects on the systems that are actually running in the buildings themselves. So it can cause motors to overheat. It can cause monitors to flicker. It can cause additional inductive loads into your building system, which affects your current that's coming into your building and affects your energy usage. So there are systems put in place that are used to prevent these harmonics from happening. The focus tends to always be on when it comes to these harmonics. The focus tends to be on motors and VSDs, because they tend to be the high load systems, equipment that are actually in buildings that are actually causing the majority of this harmonic impact to the building itself, because they could be drawing high kilowatts. They could be drawing, like I say, 300 kilowatts, depending on what system you're set up. Whereas LED lighting and televisions and whatever else, they tend to be relatively low. So VSDs are the first place VSDs and motors are the first place that energy consumption experts will be looking at whenever they're trying to improve this. So you'll see here just a sort of a little diagram of how the harmonics and power factor are affected whenever you're using a standard drive, which is a non-ultra low harmonic drive. Whenever you're running with this, and because of the harmonics that are impacted by running this, it's the true power factor that it's actually seeing is 0.78, and the line current is 128%. So let's say you're running 100 kilowatts, you're actually drawing 128 because of the impact of harmonics on your system. Now, if you're using a bit more, I suppose, the ABB drives, our standard 6-pulse ABB drives do have somewhat of a harmonic prevention through the use of a DC choke, which does help the power factor by bringing it up to 0.93. But this still has your line current at 108%. It's still not perfect. It's still not, you're still drawing more power than you need to. And then finally, we have this special piece of equipment, which is called our ABB ultra low harmonic drive. It has an active front end filter on it, which prevents harmonics from occurring. So it's a special piece of equipment that changes your true power factor to 1.0%. So you're getting your full power that you actually require, the full necessary amount of power that you require. It's actually being used on whatever it is you're trying to do, whether it be fans or pumps or whatever. So it's an important topic that's really coming to fruition in the last couple of years. So it's something to watch out for, especially if you're dealing with large kilowatt motors and maybe you're having brownouts and the like on sites that have large kilowatt pumps and fans. So in summary, over 50% of commercial buildings goes for energy consumption goes towards HVAC-R. There's legislation in place that are getting stricter enforcing people to keep an eye on their energy consumption. Building HVAC-R systems at part load efficiency should be a part of the specification. So your design should include an understanding of how your actual system works. Digital technologies are important for monitoring of what's going on and being able to see how you can improve. And then power quality, so the actual power that's coming into your network, in your system, you need to consider that and to make sure that you're using as much energy as possible on what you need it for. So a little bit about HVAC-R applications. And what applications are drives typically used on? So we see them on many things. Like I say, fans and pumps tend to be the biggest thing. So supply and return fans, chilled water pumps, compressors, cooler fans, cooling towers. They tend to see a benefit of using a VSD where part load is important for the actual running of the system itself. So here's an example of a liquid cooler fan. What do they need to do? It needs to keep the condenser water and temperature constant. It needs to prevent unnecessary cooling. How does it do it? The water temperature can be measured and fed directly in the drive. You can do that directly without using a PLC if you know how to set it up. And then the fans can be controlled with integrated PID loop controllers to provide a constant temperature. So that gives constant feedback to the drive to tell it to speed up or slow down as necessary. And that ensures that you're not running at full speed all the time, cooling water when it's unnecessary. Here's another one, a circulation water pump. And what does it need to do? It controls the temperature or pressure differential of the system. How can VSDs help? The water temperature or pressure is measured and fed directly into the drive. So again, sensors can be fed into the drive, and the pump speeds again can be controlled with PID loop controllers, giving feedback and telling it when to speed up, when to slow down. Chillers are another form where VSDs can help in the application itself. So the compressor motor needs to be optimized to meet the actual cooling demand. It needs to make sure that lubrication is working okay, and there can be different challenges depending on what the specific compressor type are. So how VSDs can help: the compressor speed is controlled according to the suction pressure itself. And yeah, it's just about maintaining the correct speed and ensuring you're running at the peak efficiency for what the system itself requires. Again, supply and return extract fans. The requirement of these is to keep cooling demand in the room at different times and days of the week. So they need to be programmed in a way that it can turn on when people are actually in the building or whenever it's actually required. And yeah, VSDs can be used to vary that speed at those specific times and run on specific timers so that they can switch on only when they're actually needed and turn off at night time or during holidays and that type of thing. So it gives you just another level of control, so you're not wasting energy when it's not needed. What are the advantages? Look, there's a number of advantages here of using drives in HVAC-R systems. The main one, as I keep saying, is energy savings. So you can actually run at the correct peak efficiency load of your system. They also lower noise levels. So if your motors and pumps are running at full speed all the time, they're going to be noisy. If you're running them at lower speeds electrically through the VSD, it also lowers the noise. So it makes for a better working environment. You have more precise control using the VSDs, controlling the speeds. There's lower installation costs, additional control through PID loop controllers, and you can integrate into your BMS such as BACnet. You're reducing maintenance costs by using VSDs. You're lowering the speed. By lowering the speed, you're lowering the temperature on the motors. By lowering the temperatures on the motors, the bearings themselves on the motors don't need to be checked as often, and in general you're increasing the lifetime of your motors. And then there's several other advantages, but yeah, the main thing in this case is efficiency is the main thing we point towards. So energy savings with VSD system. So why do VSDs improve the efficiency at lower speeds? So there is a calculation law around this. and it's something called the efficiency laws, which shows the benefit of running these running flow at lower speeds. So these are the calculations here. So flow is directly proportional to the speed. The pressure is proportional to the square of the speed. And the power you use is proportional to the cube of the speed. Okay, so these are all part of the affinity laws. So the cube law indicates that the demand for power increases with the cube of speed. So when a pump or fan is running at half speed, it actually only consumes an eighth of the power compared to running at full speed. So you imagine a half is 1/2. So a half cubed is 1/8. So whenever you're running a pump at half speed, you're not, the level of savings becomes significant. It's like I say, it's because of the cube law. It leads to significant improvements in efficiency. So reducing the motor speed by 20%, the power required can be lowered by up to 50%. So it is very significant and something to be aware of. So this cube law is applicable to pumps and fans, those type of applications, which is why it's so important that those are considered when you're looking at your energy savings. So like I said earlier, the affinity laws apply to pumps and fans, but there are different control systems that are used. So traditionally, mechanical control systems such as throttling, where you just slow down the flow physically through a butterfly valve, bypassing, where it sort of flows back and forth around the motor itself. On-off control, so just switching it on and then switching it off as and when it needs. And then there's speed control. So this is your VSD that I'm talking about. So where can the improvements be seen? So you can see, you see here the 4 different types of control that we just talked about, and what type of levels of savings we're seeing across the pump curve here. So this is just taking a typical example of a pump and calculating these out. So you'll see that by lowering the speed by a certain percentage, I'm sorry, by 70% of the maximum. While using throttle control, you're down to 89% of the overall efficiency of the motor. You're by bypassing, you're 82%. On-off control, switching it on and off, and 70% of the time you're down to 70% efficiency, or sorry, 70% load. But with variable speed load, you're bringing it right down to 45%. So there's significant savings to removing these mechanical controls and replacing them with an electrical control. This is just sort of another example with some fans. Some fans using on and off control 50% of the time. Others using VSD control 50% of the time. So with the on-off control, basically you have 6 fans, you're switching off 3 of them, and 3 of them are running at 100% load. With the VSD control, you have 6 fans running, but they're all running at 50% load. So using the calculation that we did earlier, you can see that while using VSD load, and assuming a 1 kilowatt load across each of the fans, the actual power being used on the VSD controlled fan array is 0.75 kilowatt, whereas on the on-off control, the power being used is actually 3 kilowatt. So there are significant savings to be had when you consider what you actually need compared to what you actually have on site. So this is why we really focus on VSD control for these types of applications. So here's some energy savings in practice, some case studies that were performed by ABB across the world that showed improvements here. So this is a HVAC system for McDonald's. So whenever the HVAC was set to run at full speed for busy periods and 80% speed at other times. So the customer was expecting 40% savings by switching to a VSD system, but got 50% in reality, so it exceeded their expectations. So, and additionally to that, they had reduced noise, which wasn't part of their plan, but it was an additional benefit and helped with customers on site and for their neighbours in the vicinity. Another case study here was for a Danish company. They recently changed their refrigeration cabinets so that they implemented the use of doors on their freezer units. Now, this significantly improved their energy consumption by containing the coolant within the freezer units. However, because of that, the coolant systems were actually oversized for the new setup, and it meant that the compressors were start-stopping all the time. So to address that, they added variable speed drives to the compressors, enabling them to operate at partial loads and to only switch on whenever they're actually required. So that improved efficiency, and it also minimized wear and tear on the compressors themselves by preventing the start-stop cycles that could cause damage over time. So the supermarket chain implemented the system in 132 stores and plans to install an additional system throughout 2025. So that was a good example of how VSDs can improve systems. And here's another one from Manchester Airport in the UK. So they were upgrading their AHUs, their air handling units. And yeah, they were replacing 95 different air handling units throughout their terminals, and they use BACnet to communicate with their building management system. So the condition of their air filters contributed to their energy consumption. So they were seeing a lot of dirty air filters, and that was blocking up the systems and causing pressure differences and causing increased load that was unnecessary. So they decided to monitor their systems through the drives. So they were set up in a way that whenever the pressure difference exceeded a certain limit, the drives would fire a relay and send reports back to the BMS systems, indicating the maintenance team needed to go out and clean them up. So that was a mechanical, I suppose, a monitoring and an added value through monitoring of the system itself. And it means that maintenance were notified quickly, and it saved 4,000 megawatt hours a year and cut CO2 production by over 2,000 metric tons. So it's a significant saving, can be seen across some of these bigger sites. Yeah, so that's the most part of VSD. So I'm going to talk a little bit more about efficiency of motors now. So at ABB in the motion department, I'm involved with both VSDs and motors. So motors themselves actually consume over 45% of the world's electricity, and by 2040, those numbers are expected to double. So it's an industry that's growing and growing and growing. So it's been estimated that if all 300 million electric motor-driven systems in operations were replaced with high-efficiency equipment, the global electricity consumption could be reduced by 10%. So, the numbers are very large and are only getting bigger. So it just shows the importance of making sure that we're using the most efficient technology possible on our systems. So these are the legislations that are currently in place for AC motors that are used typically on pumps and on fans. They have changed relatively recently, which some people may or may not be aware of, but the most modern one is here on the right-hand side, which was a new introduction that came out in July 2023. So this graph here shows the efficiency levels that are required for any motor that's being sold across a kilowatt band at the minute. So basically you've got IE4 here, which is the newest introduction. IE4 is a requirement. So if you're buying a new system now, it's an EU requirement that the motor, if the motor is between 75 kilowatt and 200 kilowatt, and between 2-pole and 6-pole, and generally 2-pole and 6-pole, that's a typical speed for an electric motor. They have to have an efficiency level of IE4. Outside that band, between 0.75 kilowatt to 1,000 kilowatt, you're looking at IE3 level efficiency, and below 0.75 you're looking at IE2. So this is a regulatory requirement for all motors that are being supplied in any industry in EU. Previously, before this, it was IE3, which covered 0.75 up to 1,000, and certain ones weren't considered traditionally, maybe 5 or 10 years ago. EX motors for explosive environments, they weren't considered. They are considered now because of some of these new steps of legislation. Brake motors, again, originally were not considered. They are considered now, so that's something you have to keep an eye out for. And there used to be a way of getting around it where if you use an IE2 motor with a VSD, you could continue to use your IE2 motor. However, you're not supposed to do that anymore. And the requirement is to use IE3 or IE4, depending on what your kilowatt size is. So it's a requirement. It's been pushed by the EU, and yeah, it is. Overall, it's intent. The intention is to improve efficiency in the long run. Another little thing I'm going to talk to you about is ABB synchronous reluctance motor. So whereas the regulations themselves only go to IE4, and IE4 is the minimum requirement of motors between 75 kilowatt and 200 kilowatt, there are even more efficient motors out there. So some typical end users aren't happy with meeting just the minimum requirements of that legislation. They want to push out and look for the most efficient that they currently can do to reduce their bills, to put them at the forefront of efficient technology. And that would be, with ABB, that would be our synchronous reluctance motor. So this is our IE5 motor. It's ultra premium efficiency. It meets IE5 requirements, even though the regulations currently only go to IE4. What is IE5? Generally, the steps in the IE regulations between IE1, IE2, IE3, IE4, generally each one of those steps have a 20% reduction in losses across the motor. So IE5 will have 20% less losses than an IE4, and an IE4 in turn will have 20% less losses than an IE3. So this IE5 is at the forefront of our efficiency technology, and they offer improved reliability, improved lifetime. What I was talking about earlier, because they are more efficient, because they are running at lower temperatures. They have improved bearing lifetimes. They have reduced maintenance needs. The SynRM motor, which sometimes these are compared to different technologies, and our particular SynRM motor has a magnet-free design, which enhances motor reliability and minimizes service requirements. And also from a circularity point of view, it has less internal components that can come from less ethical places. So it doesn't require any specially parts that some other permanent magnet motors may require, for example. These are drop-in replacements for regular motors, so they follow the same IEC standards, the same IEC frame sizes. They can easily switch out with an IE4, an IE3, and IE2 that may currently be in there. So it's just a plug-and-play sort of replacement. And because of the way they're designed, again, the efficiency, they're quieter. They run a lot slower than, or sorry, they run a lot quieter than a typical motor, and thus improve the working environment. So why are they more efficient than a typical induction motor? Because they have no magnets in the winding design here, or sorry, in the rotor design here, compared to a typical squirrel cage induction motor. It has a separate rotor design. This separate rotor design is specially made such that there is an elimination of rotor losses. So the way the squirrel cage induction motor design works, there is an induced motor going across the rotor bars themselves. That induced motor causes heat, and that heat reduces efficiency. But because of the special design of the rotor here in the SynRM motor, there are no rotor losses, which means better efficiency, longer bearing lifetime, and less heat losses. And that's why, again, what I said earlier about about 20% less losses between each IE band. In this particular picture, you're comparing it with an IE3, so it's got 20%, 40% less losses than an IE3. So earlier I was talking about a little bit more about running a part load when it comes to your motors. Any motor that you have will have a nameplated efficiency stated on the nameplate itself. That efficiency is based on 100% load at 100% speed. But like I say, very few systems, very few applications actually run at that load and speed. Typically, you're running at 70%. Something further, maybe even further down. So a typical 4-pole motor will run at 1500 RPM. And this graph just shows a a direct comparison of an IE3 induction motor against a Cinerem IE5. And if you're running at lower speeds, if you're running at 750 RPM, which is 50% speed, you can see there's a significant improvement. You're talking maybe 6-7% efficiency saving due to using an IE5 motor in those sort of circumstances. So it means it's an ideal upgrade option for standard induction motors on pumps and fans. And it will offer you an improved efficiency and improved savings over the lifetime of the motor. This is a typical IE5 Cinerem drive and motor package that has been compared over the last few years. So in this application, we're looking at a 110 kilowatt motor with a typical energy consumption of 8,700 hours a year, 75% power, and we're looking at energy costs here. So this sort of shows how the energy cost has changed over the last few years and the potential savings that there are to be made. So in 2021, if you were to buy an IE5 motor against an IE3, you'd be looking at 4,700 euros of savings a year because of the improvements of efficiency between the two. That in turn would give you a 5.1 month return on your investment. So if you're deciding between an IE5 or an IE3, if you buy the IE5, okay, it's going to be more expensive, obviously, but because of the savings of running in this typical application, in 2021, you would have received your money back in 5 months' time. In 2023, because of the shift in energy prices and the fact that energy prices have gone up and up, that's gone even further now. The improvement, or sorry, the return on investment you would actually see in 3.8 months. So as because of the changes in energy prices, there is significant savings to be made by moving over to an IE5 package. And although, yeah, you have to consider the initial IE5 outlay for buying the most efficient technology, it's important to understand that through the lifetime of that motor, you will see savings, and it should certainly be considered, especially for any greenfield projects that you have out there that you want to meet modern efficiencies and then some. So like I say, you're talking 40% lower losses than IE3, and 30% energy saving with our variable speed drives. Yeah, it's the way to go on any modern kind of applications that are out there. Yeah, I suppose that's the majority of what I've been here to talk about. Yeah, feel free to ask me any questions, and I'll do my best to answer them. Thank you.
That was great. Thank you very much, Chris. Take yourself a well-earned glass of water for yourself there. So I'm just going to try and pull that up now. It's from Martin. Where fans have integrated AC motors, can ABB's AFE drives still be used? A lot of acronyms there.
Oh, I don't believe so. No, I think that I think EC motors work on a different system. I don't think that we can generally EC motors. We don't have any EC motors, I suppose, at ABB, and generally we do see a lot of EC fans out there, typically in data center applications and on fan applications for fan arrays, and it is a very popular source of cooling for those applications. I've never seen a ULH drive being used on one of them. I don't think they can be used on it, if I'm being honest. In general, when we're comparing EC fans to our motors and drives, we have a difficulty comparing the two because the technologies are slightly different, the way that they actually run their fans. We tend to look at the lifetime of the motor itself. Some of those EC fans, they tend to not have the lifetime of the motor of the EC fans tends to be around the 5-year mark. Generally, when we're looking at our ABB motors and drive systems. We work on a system that leads the lifetime of those motors and systems around the 20-year mark. So it can be difficult. I suppose to answer the question in short, I don't think so. I'm not aware of any systems that EC fans that are running on ULH on ultra low harmonic drives. Um, um, no, so you'd probably have to switch to an AC motor, and it would you'd have to design your fan around that.
Thanks very much. That's excellent. Because I have a question around IE5. We look to think you're showing IE3 and IE4, and I think they said there's 20% energy saving generation to generation from legislation to legislation. Do we have any idea when we'll see IE5?
It's not there yet. There's a bit of a there's a difficulty with the legislation going from IE4 to IE5. The difficulty is that IE5 um IE5 motors tend to be run via VSD. So one of our SynRM motors specifically are run via VSD. They're only able to operate via VSD. The legislation previously, IE1 to IE4, has always been around DOL, direct online running. So the motor's running directly without a VSD. However, the legislation is starting to catch up. There's now a new legislation, which I have written above me here. It's the IEC TS 60034-30-2. I wouldn't know that off the top of my head, only it's written in front of me. But it's a new, I should say it's not a regulation yet. It's a technical data sheet that's been released, and it allows comparison of IE5 motors compared to IE4. So whenever you're considering your IE4, IE5 motors, you need to consider the system efficiency too. So you need to consider the efficiency of the drive. Now, the efficiency of a drive is very good. It's 98%, but it's still not 100%. So you need to consider that as a whole. To answer your question, is it coming out? There's no date for it set to come out. It will come out because that's the way legislation works. It moves from time to time, but there's certainly no date set for when it's going to come out. I should point out as well, ABB are working on an IE6 motor at the minute. That's going to be available soon. So these things are progressing from a manufacturer level. So at some stage, the decision will be made to move it on. And it's just an ever progressing efficiency technology improvement.
Excellent. I have another one here, and it's from John. And I know, Martin, you threw the second questions. We'd see if we can get that if we have time. Is software available that optimizes the system, for instance, using higher pump speed, leading to reduced approach temperature on the HX, but with reduced compressor power? How to find the optimum question.
It's software
available.
See that,
if you want to see that in the chat, maybe read that again in the chat. Yeah, I'm just having a read
through here. Is software available that optimizes a system, for instance, uses higher pump speed, leading to reduced approach temperature on HX, but with reduced compressor power? How to find the optimum? I probably couldn't answer that for you. That is probably a question for the compressor companies themselves. We would work with a lot of compressor companies on the continent. I wouldn't be working directly with some of those compressor companies. I would imagine that they would work in turn with maps and graphs that kind of show where the peak efficiency points are across the curves that would pick out those points. Is software available? I'm not sure. ABB don't offer it, I suppose, is the short answer. We have software that you can use to control the VSD, to tell the VSD what to do, to monitor what the VSD is doing, but it would be up to, I suppose, the compressor designer themselves to incorporate that perhaps into their own software, into a PLC, into some system that would test and then find out what the optimized solution would be for their particular compressor.
That's fine. So thank you there, come in from John. So I suppose the other question here is, and I'm how long is a piece of string? Have you got time to briefly explain how magnet-free motors work?
Oh God,
can we condense that one down to think, or without a whiteboard?
You've probably caught me out a little bit there. I have some slides on that, but I probably won't be able to find them right now. basically,
if you want to send them on afterwards, we
yeah, I
can
can send them on afterwards, and I'll send them to Jeff afterwards, and perhaps you can send them on to Martin, sort of, to explain it. Effectively, the SynRM motor that I'm talking about is a synchronous motor, so it runs via VSD. It has zero slip. So the way that an induction motor works is that there is always slip between the rotor and the actual magnetic flux, and that slip provides the power to the shaft itself. The way a SynRM motor it works is different. It's a synchronous reluctance motor. It works with zero slip. Can I answer how it works? At a time I could. I just don't have it off the top of my head now. And like I say, if I'll get the slides together and I will send them over to you later, send them over to the team later, and we can share them that way. Is that okay, Martin?
That's perfect. Yeah, he said slides will be great for later, so he's happy enough with that. Okay, well, look, I don't see any more questions. Check the Q&A, check the chat, so that's fine from us. I think that was very good, very enlightening. I thought I enjoyed it anyway. And I said the slides will be available afterwards. There are people out there. If you're not a member of the IRI and potentially you'd like to become a member of the IRI, get my own plug in here, Chris, please do reach out to myself or Karen in particular. And again, I want to thank Chris I thought it was very good. I really enjoyed it. Lots to do. As I said, you might use 1 or 2 slides myself going forward, if that's all right. Of course, we'll give you the credit for my own presentations and EVACs, but look,
I'll send you an invoice.
Very good. I thought it was very good, yeah, and I can see people coming in saying well done as well. So look, really good all around. And again, I was thank you for joining us, and thank our sponsors as always for sponsoring the IRI. And again, anyone out there who would like to become a member or like more information on the IRI, and please do log on or get in touch with us. And I said we'll have more and more coming through. And again, look, from Chris' perspective, from ABB's perspective, we'll pass on his details if you've got some jobs coming up or anything like that. This is your plug, your brutal plug here, Chris. You please, by all means, get in touch, and I'm sure he can sort you out from that front. All right.
Absolutely. And
thank you very much.
Thanks, Jeff.
Everybody.
Thanks, Karen. Thanks, everyone who listens. All the best.
Have a great day, everybody. Thanks so much. God bless.
Thank you.
Bye-bye.
Bye.
Bye-bye.